for the invitation. So, as the title says, what I wanted to speak about today is about graded homotopy classification of Leavitt path algebras. And even though this is organized by a Leavitt path algebra group, I figured we could start by setting some common conventions. So I'm going to briefly recall the definition of a Leavitt path algebra and then move on to this problem that I am interested in talking about. So I will start with L commutative ring equipped with an involution, which I will denote star. So the main example to have in mind is the complex numbers with complex conjugation, but we could also take, for example, star to be the identity and L to be any other commutative ring, say the integers. And well, as most of you possibly know, Leavitt path algebras are algebras constructed from graphs. And for us, graphs are built by two sets of edges and vertices and two pair of functions which determine where does an edge start and end respectively, as in the picture. So an edge E starts at S of E and ends at R of E. And in this talk, all of our graphs will be finite, meaning they will have a finite amount of both vertices and edges. And also for simplicity, we will assume that L is a field. This is not necessary everywhere, but it is a safe assumption for what we are about to do. All right. And so yeah, so the Leavitt path L algebra LE, as a graph E, is a certain quotient of the path algebra, not of E, but of the double graph of E. So one starts with a graph E, then for each edge adds formally an edge in the opposite direction. This is the edge E star in the picture associated to E. Then one builds the path algebra construction. And finally, we mode out by some relations, which are specific to the Leavitt path algebra construction and which have to do with the dynamics of the graph. So it is that sort of algebra. I'm not going to go talk about the full definition, but the only thing we will need today is that it is generated by vertices, edges, and this formally added edges. And some other facts that it satisfies, the main one being Leavitt path algebras are graded over the integers. And the way to do this is to grade them over the generators. So we decree that vertices have degree 0, edges have degree 1, and these edges we added formally in the opposite direction have degree -1. And this in fact gives a grading over Z of the whole algebra, which is in fact the grading given by length of paths. Every path in E can be viewed as an element in this algebra, and it's a homogeneous element whose degree is precisely the length. So this is the main structure that we will care about in this talk when talking about Leavitt path algebras. And then let me just briefly do this. There are also star algebra. This assignment between original edges and the formally added ones gives you an involution. So actually extends the involution of L to the whole algebra, although this will not be very important today. And just in case you haven't seen them before, some examples would be matrix rings over the base ring or polynomials over that ring, Lorentz polynomials actually. But then more typically you have infinite dimensional examples such as the free algebra on one element that has an inverse on one side, or well, Leavitt algebras, which are these family that don't satisfy the basis, the invariant basis number property. Right, so anyway, these are Leavitt path algebras. We will think about them as graded algebras at all times. So we will be caring about them with their grading. And the question I wanted to say something about today is the graded classification conjecture for Leavitt path algebras. So let me first state what ingredients does it involve, and then I'll say what the conjecture precisely states or says. So the graded classification conjecture states that Leavitt path algebras can be characterized, again, as graded algebras by their graded Grothendieck group. And this is an abelian group. In fact, one can construct it as follows. One can take the free abelian group on isomorphism classes of graded projective modules, and then we divide by the relation that the sum of two classes is equal to the class of their direct sum. And so the conjecture, I'll state it precisely in a minute, but what it says is that every question you can ask about LE, which involves its structure as a graded algebra, should depend only on this group associated to it, which in principle should be much easier to understand than the algebra itself. But to say this precisely, one has to speak about some extra structure that this group has. So first, it has an action from the group of integers, so an infinite cyclic group. Now, to avoid confusion, I'm going to denote that say infinity. So by that, I mean just an infinite cyclic group with a generator sigma with multiplicative notation. It's just so that I don't mix it up with Z. And the action is given by degree shifting. If I have a module, it decomposes as the sum of its homogeneous components. So if we shift them one by one, we get a new module. Actually, as a module, it's the same, but the gradient is different. And this actually induces an action on this abelian group. So it is, moreover, a module over Lorentz polynomials, a module over the group ring of Z infinity, which I will typically denote Z of sigma from now on. Right, so that's the one extra structure this abelian group has. And another one is it has a distinguished submonoid. So in this group, we can take classes of projective modules. We can both sum them and subtract them. One thing we can consider within it is taking classes of projective modules, but only summing them. So only considering the submonoid generated by that. And well, that is one thing one can consider. And further, an element there, a very distinguished element there, is the class of LE itself. Since it is a free module over itself, it is projective, and it lies further not only in the graded Grothendieck group, but in this submonoid, which I don't know if I said it, but it is sometimes called a positive cone of the graded Grothendieck group. Right. So with all of this structure in place, one can state the conjecture more precisely. This is due to Rusbe Hasrat. I think the paper was published in 2013. So what the conjecture says is that if E and F are two finite graphs, then the associated Leavitt path algebras are isomorphic as graded algebras if and only if the graded Grothendieck groups are isomorphic, but preserving all of this mentioned structure. So there must be an isomorphism that maps one of the positive cones to the other positive cone, and it maps LE to F, the class of LE to the class of F. All right, so we're not only considering these as just abelian groups or just considering the action, we're considering all the lists of properties. Okay. So today, I wanted to talk about weakening of this conjecture. So what I want to talk about is the graded homotopy classification conjecture. Excuse me. Right, sorry. So I will speak about a weakening of this conjecture, which I have named here the graded homotopy classification conjecture. And so I'll say why we care about this in a minute. But roughly speaking, it's the same conjecture, but instead of classifying things up to isomorphism of graded algebras, we will classify them up to a weaker notion, which is graded homotopy equivalence. So let me define what that is. So it's a relation in graded algebras, but it first comes from a relation between maps between graded algebras. Okay, so one first considers elementary homotopies, which are things between graded algebra homomorphisms. If we have two graded algebra homomorphisms, we say they're elementary homotopic. If there is a map H, as in the picture, from A to polynomials in B, here the maps go from A to B, and this map H goes from A to polynomials in B, where T has degree 0. And when we evaluate at 0 or 1, we recover the original maps. So we can go from F0 to F1 through this map to polynomials and B. Right, so this gives a relation between algebra homomorphisms, graded ones, which is reflexive and symmetric, but it is not transitive. So one way to fix this is to consider its transitive closure. And this is the notion of two maps being homotopic. So we say the two maps are homotopic if there's a finite chain of elementary homotopies between them. And now this gives a relation between graded algebras. If we have two maps that compose two things homotopic to identities, we call them homotopy equivalences, and we say that two algebras are homotopy equivalent if there is a graded homotopy equivalence between them. Right, so the conjecture then, the weakening of the graded classification conjecture can be then stated in this new language as follows. If we have two finite graphs E and F, then the following statements are equivalent. One, there is an isomorphism between these graded Grothendieck groups that preserves all the relevant structure. And two, instead of having isomorphisms between the algebras, we have two maps going both ways. And the compositions are not the identities, but homotopic to identities. Right, so if the original conjecture holds, then this holds. And what we care about is saying whether this holds in some cases and then seeing the difference between this and the original conjecture. So namely, this sort of result comes from the ungraded classification conjecture. So actually the motivation for such a result comes from the ungraded classification of Leavitt path algebras, which in itself comes from the classification of C-star algebras, graph C-star algebras, in which I don't want to speak too much about C-star algebras because I'm far from knowledgeable on them, but one first does a classification of the homotopy and then bridges the gap between homotopy and isomorphism. And here, this program aims to do the same. So we want to first say something at the homotopy level and then check whether homotopy and isomorphism are different or not. I mean, homotopy equivalence and isomorphism are different notions or not. Okay, so what I want to talk about today is about this part, the homotopy part, so checking this weakening of the conjecture for a specific family of graphs. Which are primitive graphs. So I will say why I need my graphs to be primitive in a minute, but let me first tell you what the definition is, or recall it. So the definition can be given in many ways, one of which is in terms of the adjacency matrix of the graph. And so recall that this is a matrix indexed by vertices, which in the B, W entry has the amount of edges from B to W. And sorry. Okay, and has the amount of edges from B to W. And in terms of this matrix, a graph being primitive means the following. There is a power of the adjacency matrix such that all of the entries are positive. So what this means is that there is some n such that for each pair of vertices, we can connect them through a path of length n, and this number does not depend on the vertices chosen. So in a way, this is like a connectivity condition. We want all vertices to be connected to each other, but further, we want them to be connected uniformly. We can pick a fixed length, and independent of the vertices chosen, we can connect them through a path of such a length. I think I should get some more water just in case. So if you allow me, I'll do like a minute pause.
No worries.
Okay, I'll be right back.
Okay.
Sorry, I'm back again. Sorry for that. But okay. So as I was saying, we want to verify this weakening of the graded classification conjecture for primitive graphs, and primitive graphs can be defined, for example, through the adjacency matrix, and we can think of them roughly as highly connected graphs in a uniform way. So here I have an example, which is the rows of two petals. Its adjacency matrix is positive to begin with, so there's not much to do. And then the non-example is actually a very straight non-example. That graph is not primitive because it's not even reducible. I mean, you cannot even connect each pair of vertices because the only arrow between the vertices that you have goes exactly one way, but there's no arrow in the other direction. And this directionality is actually relevant. One can also check in the matrix. This matrix is upper triangular, so there is no power of it that will have a positive entry where you see a zero. So at least in the story examples, one sees that the important thing to care about is connectivity, but further, actually, primitive graphs are not only very connected, but in like a uniform way. One can also describe them in terms of the period of the graph. In any case, what we'll do today is verify this weak conjecture, this graded homotopy classification conjecture for this family of graphs. And let me tell you why. So, as I was saying before, the story comes from ungraded classification of Leavitt path algebras, and specifically from the homotopy classification of Leavitt path algebras in the ungraded case, which is done for purely infinite simple ones. And in that case, the fact that these are purely infinite simple gives you a lot of nice tools, at least related to the things that we'll do today. And so we need some sort of simplicity hypothesis in the graded setting. Concretely, what we mainly use, but I think this is most likely equivalent to it, is that if E is a primitive graph and you have an edge, then the idempotent EE star associated to it is a full idempotent in the degree 0 component. So you can get one by multiplying elements to EE star and summing, but you can also choose them to be of degree 0. This is much stronger than just saying that this is a full idempotent in LE. It is a full idempotent in LE0. And this is actually something we use, and that in the ungraded case, every idempotent is full if your algebra is purely infinite simple. So that was for free, but here the conjecture is for all graphs. So to adapt the tools, we had the necessity for some simplicity assumption. And well, as I was saying, the goal will be to prove this graded homotopy classification conjecture for primitive graphs. Okay. Right. So the main tool to do this for us will be graded bivariant K-theory. And let me tell you a bit about my plan for the rest of the talk. So my idea here is to present what this thing is in a minimal way. So saying the least amount of things one needs to know to work with it. And then present a brief argument of the proof for this conjecture, as in what are the steps that are needed to prove it. And then maybe going a bit step by step in the proof, but only in the statements that I think would be of general interest. So not exactly the technical ones, but the things that one could export and maybe speak about in other contexts. But everything essentially stems from this graded bivariant K-theory. So I wanted to first give, I don't know why we call this a definition, but at least a characterization that lets you work with it. Okay, so the conjecture we care about, even the non-homotopy version, so the original graded classification conjecture, is something about this assignment that is on screen, which is for each graded algebra homomorphism between LE and LF, we can view what it does at the level of graded Grothendieck groups. And our question is, if there is an isomorphism lying in the right-hand side, do we have an isomorphism on the left-hand side? So to understand this, we could more generally understand how this assignment works for every pair of Leavitt path algebras. And this should, if we fully understand this, we should say something about the conjecture itself. Okay, and so this assignment actually comes from a functor, the graded Grothendieck group functor, from the category of graded algebras to the category of, say, modules over Z of sigma. So modules, abelian groups with an action of the integers. Of course, in the conjecture, we actually care about extra structure. These modules are ordered and they have a distinguished element, but at least naively, this is an assignment from graded algebras to abelian groups with an action. And so the idea or the proposition is to consider an intermediate category. So something that sits between algebras and groups and that factors graded K-theory. So I will say what this is in a second, but the diagram should look more or less like this. We have an assignment from algebras to groups, which is graded K-theory, the graded Grothendieck group. This is now the curved arrow. And we want to pass between an intermediate category. So a category in which we maybe gain some more flexibility. So concretely, KKGR, I will omit the GR, speaking at least, will be a category. And we will have a comparison functor between algebras and this category. And it will allow us to decompose the assignment of graded K-theory in sort of two steps, passing between this category. And we'll try to say things about Leavitt path algebras viewed as objects there. That is essentially the idea. Okay. So as I said, this is a category, so it has objects and morphisms. And the objects are relatively simple. They're the same that the category of graded algebras. Objects here are graded algebras. The complicated thing is describing morphisms between two objects here. What we for sure have is a comparison functor. So this thing J here, which allows us to view each algebra homomorphism as a homomorphism in this category. But in this category, we have more morphisms. In fact, the interesting thing about it is considering the morphisms. And although the definition of the category is very technical in of itself, it can be characterized as the smallest category that has such a comparison functor that satisfies some universal property. So in some sense, this category graded KK receives a comparison functor from algebras, that satisfies three main properties that characterize it. So KK would be a category whose objects are graded algebras, but we also have some identifications. The first one, for example, is so-called homotopy invariance, which is that if we view the inclusion of a graded algebra into its ring of polynomials, this becomes an isomorphism when we apply this J functor. So in this category, A and polynomials over A, here the variable has degree 0, are the same thing. And one can actually prove that this implies that homotopic algebra maps become the same one in KK. So this is some sort of homotopy invariance. KK does not see through homotopic maps. So for example, of course, one loses some information in this passage, but if we're interested in classification up to homotopy, then maybe this is one of the invariants one could look for. Further, this category has some type of Morita invariance. And one way to say this is that it also identifies each graded algebra with matrices over the algebra. So again, one can include A in M infinity of A in any of its corners. This is, of course, not an iso, but it becomes an iso in this category. And well, the third property is maybe a bit harder to state informally, but it is excision. And what this roughly says is that if one has a short exact sequence of graded algebras, then it produces a lot of long exact sequences between them. Formally, this category KK is triangulated, and this short exact sequence gets mapped to a triangle in the category KK. But very, very informally speaking, one can produce a lot of long exact sequences out of short exact sequences of algebras. Okay, so KK is in some sense the smallest category that has these three properties. One can view algebras there, and one has these two identifications and this short exact sequence, long exact sequence phenomenon. And without knowing the definition, one can actually do a whole lot abstractly with these properties. And even though this is a mixture of both things, one theorem I could tell you about, which does not use as what is in there, is that, for example, maps between the base ring and the Leavitt algebra. Well, this is an abelian group actually, because the category is additive, and it recovers precisely the graded Grothendieck group. So for example, this category intrinsically encodes the graded Grothendieck group as some morphisms there. So the morphisms here are really interesting. In fact, they codified graded Grothendieck groups. And well, the second thing is we have maybe some hint that this was an interesting invariant to consider for homotopy classification. And further, we have a sort of strong classification result if one considers classification in this category. So if one wanted to classify Leavitt path algebras instead of as graded algebras as objects in this category, then this can be done, and it only depends on the graded Grothendieck group as a module. So if you only care about the Grothendieck group, the graded Grothendieck group as an abelian group with an action, you discard the positive cone and distinguish element, then that information is enough to recover the Leavitt path algebra as an object in this category. Of course, then one has to check what the difference is between classifying here and classifying at the algebra level, which was the thing we were actually interested in the first place. But this is sort of how the argument goes. We'll say things about Leavitt path algebras at the KK level, and then try to translate that about some sort of statement at the algebra level. So at the strict grade algebra level. All right, so one last thing I should say about this KK is that this J functor is actually the identity on objects. So both the category of algebras and KK have the same objects. their different systemorphisms. But this comparison functor maps an algebra A to A itself, but viewed as an object in this KK category. So I will often drop the J from the notation because it really is the identity in objects. What it does in morphisms is the complicated thing. Okay, so far so good. At least we have presented this category. Now, what we want to do is to understand whether the graded Grothendieck group classifies Leavitt algebras up to graded homotopy equivalence, say, or if we're lucky, up to isomorphism. Our proposal was pass through this intermediate category and try to understand maps between Leavitt algebras in this category with respect to maps between the graded Grothendieck groups. This is still hard enough, but at least, well, we have an aim. So we could first try to understand this and then see how this compares to the algebra level. So as I said before, if one only considers the abelian group class action information, one can recover Leavitt algebras up to ISO in this category. But actually, we want more. We want to understand all the possible morphisms between them. And to do this, the main result that we will use is this sort of universal coefficient theorem, which is this theorem on display. It has a lot of symbols, but what one should take away from this is that in the middle, we have this group we want to understand. Morphisms between LE and LF in this new category graded KK. And what we can do is express them in a short exact sequence where all of the other terms are either graded Grothendieck groups or graded K1 groups, which one would hope are a bit simpler to compute. So only one caveat is on the left, we have to consider actually a dual graph. So in the left-hand side, we have the graded Grothendieck group of the dual of E, which is the same graph, but with all of the arrows reversed, tensored by the graded K1 group of LF. Then there is some mysterious map partial to the group we're interested in. And then we have this evaluation map to graded K theory. Okay, and what we want to do is understand the relationship between algebra homomorphisms, KK homomorphisms, and homomorphisms between the graded Grothendieck groups. So to this short exact sequence, one could add to the diagram the graded algebra homomorphisms, and then we have a diagram as follows. The curved arrow is actually what we're interested in, which is the graded K theory assignment from algebras to groups with action. This factors through this category KK. And this group, the KK homomorphisms between LE and LF, are related to, well, again, graded Grothendieck group homomorphisms plus some kernel, which seems to be the difficult part to understand. Okay, and so what we will do is we will actually show that there are homotopy equivalences coming from isomorphism of graded Grothendieck groups in 2 steps. So what I want to do here is I'll tell you what the recipe is. I want to tell you why this recipe works. And then the main ingredients to group each step in the recipe. So there are 2 steps to this argument. First, if we have a map and KK, so something in the middle of this row, which when mapped to the right, gives you an honest pre-order module map. So not any module map, not any abelian group map preserving the action, but also preserving the order and the distinguished elements. Then this arrow in KK actually came from an algebra homomorphism. It was actually of the form J of F for some F. So this is some sort of surjectivity statement. For the arrows that we care about, which are the ones that induce pre-order module maps at the level of K theory, we have that they are of the form J of F for some F. And then this is some sort of surjectivity statement. Likewise, what we also want to do is some sort of injectivity statement. So what that would look like is if we have to create algebra maps between Leavitt path algebras, and they are mapped to the same in graded KK, then they're very similar in a very precise sense. So they're not homotopic, that's what one would wish, but they're almost. One has a unit such that conjugating one of the maps by that unit is homotopic to the other. So that is essentially the two key things that we have to prove in order to get homotopy classification. I would assume this gap between these two things and the homotopy classification is not clear just from the statement. So that is what I wanted to do first. So first I want to see, before getting into why these things are important or how they could be proved or what tools are used to proving this, I want to say why these two things actually prove what we wanted to prove in the first place. So let me just briefly say it again. What we want to do, this one and two statements are as follows. If we have a map in KK, which induces a pre-order module map, then it comes from an algebra map. And two algebra maps are the same in KK if one is homotopic to a conjugation of the other. Now, I want to use these two things to actually prove the conjecture. So let's see why 1 and 2 together imply that the graded Grothendieck group in fact classifies Leavitt path algebras up to graded homotopy. I should recall again that we're doing all of this for primitive graphs. So here I should say for primitive graphs everywhere, but I won't. This is implicit, at least for me. Okay, so let's see how the proof goes. We will start with an isomorphism at the graded Grothendieck group level. So a pre-order module, pointer pre-order module map at the graded Grothendieck group level. Now, something that we had known for a long time, in fact, is that we can always lift it at the KK level. So we have something here, and we can always lift it to a map here. In fact, we can lift isos to isos. So this is there's nothing new, so to speak. It has a bit of time, but what we for sure can do is lift isomorphisms here to isomorphisms here. But now these new things 1 and 2 that I just spoken about now apply. So for example, the first thing is this lifting, say psi, by definition, when you look what it does at the level of graded Grothendieck groups, it gives you a pre-ordered module map because it actually was built from a pre-ordered module map. So this map psi comes from a graded algebra homomorphism. This is the surjectivity statement. Not only that, we can do the same for its inverse. So since we know that this is an isomorphism at the KK level, it has some inverse. That inverse maps to the inverse of the pre-order module map at the level of graded Grothendieck groups. So again, by this sort of surjectivity statement, we can lift it once again to a graded algebra homomorphism. So we started with some map between the graded Grothendieck groups, we lift it to the KK level, and then that map and its inverse can be lifted to the graded algebra level. And now these liftings, F and G, are essentially built so that they compose to identity, not at the graded algebra level, but at the KK level. Because on the KK level, they are inverses strictly. That is exactly how we built them. We lifted this map psi and its inverse. So these two maps, F and G, compose to identities at the KK level. So by this sort of injectivity statement, these compositions are homotopic to some conjugation by some degree 0 unit. So the fact that these are equal to the identity in KK means that they're homotopic to a conjugation of the identity which means they're homotopic to conjugating by some unit. And so what we are seeing is that there are graded algebra maps between LE and LF, and the composition of both in both directions gives you actually things homotopic to isomorphisms, homotopic to conjugating by a unit. So this is now a standard argument. Once we have reached here, then just manipulating the maps that we get, we can get that F is a graded homotopy equivalence. So this step from the step we just said something about with the last one, this is something related to when you have two maps and their compositions are iso, then each of them is an iso. They need not be inverses one of the other, but if both compositions are isomorphisms, then they are isomorphisms. So what we do here is we use this surjectivity and injectivity statement to get two maps such that both compositions are homotopy equivalences, but then both maps were actually homotopy equivalences. So with this quote-unquote injectivity and surjectivity statements, we can prove this conjecture for primitive graphs. So all of the work is concentrated in proving these two statements. And so I wanted to say what the ingredients of proofs of these statements are, or at least the parts that I think could be of use in other contexts. So for example, for this surjectivity statement, a main tool is actually surjectivity of the graded Grothendieck group factor. So what we want is to lift some graded KK maps that came from a preordered module map and so on and so forth. But a key step in that proof is actually a much simpler statement, which, if I recall correctly, was actually part of the strong graded classification conjecture, which is if we have a preordered module map between graded Grothendieck groups, then we can lift it to a map between the Leavitt path algebras, a graded unital map between the Leavitt path algebras. So that in of itself, I hope at least will be applied somewhere. And it is in fact one of the key ingredients in the proof of surjectivity for this more complicated statement of surjectivity. Now, this is not the whole proof for the surjectivity statement. One also has to understand this kernel here, this mysterious map partial. And also for K0, we have more or less a description of it in terms of the graph. And actually so for K1, but what we also want is to have some sort of description of graded K1 in terms of units. So ungraded K1 has some description in terms of units, or at least invertible matrices. And for example, if the ring is purely infinite simple, then usual ungraded K1 is exactly abelianizing the units. We want some sort of similar statement at the graded level. This is actually where the one map is homotopic to a conjugation of the other comes from. This unit lying around actually comes from some consideration of graded K1. So to recap, first surjectivity, the main thing is this lifting result, which is actually a statement not on KK, but on graded Grothendieck group of Leavitt path algebras. And then to complete the argument and for the injectivity part, we have two things. One, to understand this map on the left, and also to have some description of K1 in terms of units. Okay, so for these two things, we have some results. The first one is the one I'll be less specific about. So to understand this complicated map partial, the main thing was to have a graded analog of an algebraic version of so-called Poincaré duality for Leavitt path algebras. So I think if Willie's in the audience, maybe he knows the original reference, but there is a sort of Poincaré duality statement for graph C-star algebras. Then recently he adapted it for Leavitt path algebras in the ungraded setting, and we actually needed an improvement in graded bivariant K-theory. So the main thing to understand this map is this theorem we have in display. I will say how this connects to the things we have said in a minute, but What it says essentially is that tensoring by LE and tensoring by L of the dual graph are adjoint functors. So if you want to understand morphisms between a graded algebra tensor LE to a third algebra in KK, you can pass the graded the Leavitt path algebra from the left-hand side to the right-hand side, paying some prices. You have to change the graph by the dual, and there's also some shifting, something along the lines of the well, yeah, so something that has to do with a triangulated structure, but roughly speaking, you can the duality is duality in the name comes from the fact that you can pass from LE to L of the dual of E in the left-hand side and in the right-hand side, respectively. And the case that is of interest to us is exactly when R, the graded algebra R in the theorem is just the base ring, so L, so that tensoring by L does nothing. And S is the Leavitt path algebra of another graph. So if we do that, then on the left-hand side, we have KK homomorphisms between LE and LF. And on the right-hand side, we have maps between the base ring and something that has to do with LE tensor LF. And one actually can check that this is essentially graded K1 of the tensor product. Here, sorry, this should be E dual. There's some H going on. I won't be very precise, but this is like a homotopy invariant version of K theory. And so we can compute graded KK maps as some homotopy graded K theory group, some KH1 of LF tensor LE dual. So although this may look as like complicating the setting even more, the point is that this map partial, let me go back for a second, was a map between K0 and K1 of the Leavitt path algebras mapping to this group. And now through this theorem, we can identify this map to something that both starts and ends at graded K theory groups of things related to Leavitt path algebras. So we replace the codomain by, again, something that is essentially a graded K theory group of Leavitt path algebras. So although this is perhaps a less related element in the talk to the rest of the things, I wanted to mention it just to say that actually one of the key technical points in the proofs was proving this statement in this generality. And most of the technical effort, or at least a good chunk of the technical effort, was in proving this. It is not very explicit when one writes down the argument, but it is actually there, and proving that it held in the graded setting involved a lot of technicalities with graded KK. But now, back to the things that I think could be more generally applied. So this was to understand this map partial. The other thing I was talking about, let me go back again, is that we wanted some description of this K1 group in terms of units, or some sort of graded units. And this is a problem I could state in full generality. And for an arbitrary graded ring R, a description of K1, graded K1 in terms of units, is not as satisfactory as in the ungraded settings. So for the ungraded K1, one has a description in terms of invertible matrices. For graded K1, right now, I'm sorry, I'm missing the reference, but there is a paper on it that has some sort of local description in terms of matrices, but it is not quite as satisfactory as in the graded setting. And further, we are adapting techniques from the purely infinite simple case of the ungraded conjecture. And in that case, K1 is precisely units abelianized. So we want some sort of statement along those lines. We really want this to be units, perhaps with some extra condition, but essentially units. So as I said, for an arbitrary graded ring, we're possibly hopeless, but we can do this with some extra assumptions, which our algebras will satisfy. And this is a statement on K1 of these algebras. So recall that a graded ring is strongly graded if one takes two homogeneous components and the product, say, of the graded component of degree k with the one of degree L is precisely the one of degree k plus L. So our ring is graded if it satisfies a bunch of conditions, and here we have an inclusion. So a thing of degree k times a thing of degree L has degree k plus L. A ring is strongly graded if that inclusion becomes an equality for each k and L. So that is, for example, one thing that Leavitt path algebras of graphs without sinks satisfy, and all of our graphs are primitive, so our Leavitt path algebras satisfy this condition. They're all strongly graded. And another condition a Leavitt path algebra satisfies is that its degree 0 component is ultramatricial. And that means it is a union of rings which are product of matrix rings. So Leavitt path algebras satisfies these two things, at least in our case. They're strongly graded, and also in general, their degree 0 component is ultramatricial. It's a union of matricial algebras. So when these two things hold, we in fact can give a description of K1 in terms of units, but units of the degree 0 component. So if R is a strongly graded ring and its R0, its degree 0 component is ultramatricial, then graded K1 is precisely the units of the degree 0 part abelianized. So in particular, this applies to our Leavitt path algebras, which were the example of interest in the talk. But the proof is simple enough to do in the general case. So let me just say 2 words about it. So one thing is, by a general theorem of Tate, if you have a strongly graded ring R, then graded K1 is ungraded K1 of the degree 0 component. So that is one step that is just general. Every time you have a strongly graded ring, you can pass from graded K theory to ungraded K theory of the degree 0 component. And now the statement becomes, if you have an ultramatricial algebra, K1 should be the units. And the way to prove that essentially is that both things, the things that you want to check are the same, respect products and respect unions. So if you know it from matrices, you know it in general, because you know it for product of matrices and then union of such things. So you know them for all ultramatricial algebras. And for matrices, one just checks by hand that this holds. So in general, we do have a description of graded K1 for any strongly graded ring such that the degree 0 component is ultramatricial. And well, I don't see how restrictive this is, but at least for all Leavitt path algebras of graphs without sinks, one could say this. Okay, but now this is as I group, right? I mean, let me go back for a second. This isomorphism tells you this group is isomorphic to this other. But we also want to understand the action. You know, at the end of the day, the action will come out. In fact, in this universal coefficient theorem we had, there was some tensoring by Z of sigma and so on. So the action will be lying around and we want to understand it. So, okay, we now have this description in terms of units, but how does the action behave? If I have a unit and I act by this sigma element, what unit do I get back? So the last thing I wanted to say is how to explicitly give a description of this action. I think, well, again, this is a statement generally on K1 of Leavitt path algebras. And then I want to wrap up by restating the conjecture that we have done. So anyway, as I was saying, we have an isomorphism by this last lemma between graded K1 of a strongly graded ring with ultramatricial degree 0 component. With this graded K1 and the units of the degree 0 component, abelianized. And on the left-hand side, the action is shifting of modules. On the right-hand side, well, we don't know yet, at least as of this slide, we don't know yet. But at least in the cases that I could say something about it, we need further hypotheses, which again will be satisfied for the Leavitt path algebras that we care about, but we could state in more generality. So let me state them in that way. So we can actually do this for corner skew Laurent polynomial rings. And those are graded rings over Z, as any other ring today, that have a degree 1 element and a degree -1 element whose product is 1. So there is a right inverse, I think. So a right unit of degree 1. I think that is the correct statement. In any case, explicitly, we have a degree 1 element and a degree -1 element satisfying this equation. Now, each time one has this, you can check that the other product is an idempotent, and that multiplying by t plus and t minus gives you an endomorphism of the degree 0 component. Sorry, yeah, here Willie says in the chat that t plus is left invertible. Okay, so each time you're in this situation, you have a map which takes a degree 0 element and multiplies by t plus on the left and t minus on the right. And that not only is an endomorphism, it is actually injective, and its image is this corner that I've written here, which is the corner associated to the idempotent t plus t minus. So what I claim is we can characterize the action on K1 for each corner skew Laurent polynomial ring, which is in addition strongly graded and has algebraical degree 0 component. So those are a lot of hypotheses, but one example of such rings are, again, Leavitt path algebras of essential graphs. So these graphs do not have sources. And again, this is guaranteed in our case because our graphs are directly primitive. So each pair of vertices is connected through some path. In particular, each vertex emits and receives an edge. So this is, again, applicable to our context. But more generally, if you have any essential graph E, and you take one edge ending at each possible vertex P, then you can make the Leavitt path algebra of E into a corner skew Laurent polynomial ring. And what you do is you take T plus to be the sum of these edges, and T minus to be the star of T plus. So there was this involution going on, but explicitly you take the sum of this E sub B's as T plus, and the sum of this E star sub B as T minus. Now the relations, the Kunst-Krieger relations that finally let you check that T minus to plus is 1, so this is in fact a corner skew Laurent polynomial ring. And the name, I suppose, comes from the fact that one can actually express an element in the ring as a sort of polynomial with coefficients in R0 and powers of T plus and T minus. Okay, so when we are in this hypothesis, we can in fact give an explicit description of the action of graded K1 of this ring. So let me just, the last thing I want to say is this. So for an essential graph and this endomorphism coming from the corner skew Laurent polynomial ring structure, we can say what the action on K1 is. And in fact, this is a generalization, not a generalization, but this is analog to an existing statement, which was due to Ara and Pardo, which says we can characterize the action on the graded Grothendieck group. So if we care about the same issue, the same problem, we have the graded Grothendieck group of LE. We view it as ungraded Grothendieck group of LE0. Then the action on the graded Grothendieck group, when we view it in the right-hand side, it comes from applying the K-theory functor to this alpha endomorphism. So at the K0 level, the ungraded K0 level, the action translates to this corner endomorphism, which becomes an isomorphism at the level of K0. So in the same sense, if we have an essential graph, then under this isomorphism between graded K1 and ungraded K1 of the degree 0 component, the action corresponds to applying K1 to this corner endomorphism. In particular, when we have a unit, we can view it, a unit in the degree 0 component, we can view it as an element in ungraded K1, and we can apply this one. Has an explicit formula in terms of alpha and the corresponding unit. So one question I have is, both of these statements actually are statements at the level of K-theory groups. So K0, graded K0 and graded K1. These are not, at least in the proofs that I've seen, these are not statements done at the graded modules level. So it's not like we prove something for graded modules and then apply graded K-theory and check that two things are the same. So it's not at the level of functors between graded modules. It is really a statement at the level of graded K1 and graded K0. So one question one could ask is, do these two statements come from a more general statement at the level of categories of modules? And so that we just apply K0 and K1 and obtain both of them. But so far, I don't know, but at least we can characterize the action in this way. And so to recap, this gives some sort of understanding of graded K1 of a Leavitt path algebra in terms of units. On the other hand, we have this lifting result between graded Grothendieck groups of Leavitt path algebras. And these two things gave us injectivity and surjectivity criterion to compare Leavitt path algebras and as objects in graded KK. And those were the main components in the proof of the conjecture for primitive graphs, which I want to state again. So with all of this in place, we have the following. If L is a field and E and F are two finite primitive graphs, then the following statements are equivalent. One, there is an isomorphism of graded Grothendieck groups preserving all the relevant structure, so the positive cones and the distinguished elements. And two, there is a unital graded homotopy equivalence between the corresponding Leavitt path algebras. And with that, is all I wanted to say. So thank you very much.
Thank you so much, Guido, for that very nice and thorough explanation. It's a wonderful talk. Thank you so much. Okay, so are there questions from our audience for Guido?
I want to make a comment on this question of Guido's in the previous slide. Of course, so one would think that for a general skewed rank polynomial ring, it should be true that I mean, such a ring is strongly graded, and so on. So it's graded K0 is K theory is the K theory of the part of degree 0, and this comes from Date's theorem. So one would expect that the equivalence, in that generality, that the equivalence comes from this endomorphism alpha corresponding to the T plus T minus. Yeah, but in the particular case, so there is a much weaker question that one could ask, which is whether at the level of K theory, and at least for strongly graded Leavitt path algebras, I mean, or say Leavitt path algebras of essential finite graphs, whether the map induced by this alpha coincides with the action of the cyclic group. And this is should be an easy consequence of the fact that graded K theory of the Leavitt path algebra is the graded K0 tensor, the K theory of the ground field. So all the action occurs at K0, and we know this is true for K0 by R and Pab.
Maybe a comment I can make on it. But one thing I think for a corner skew Lorentz polynomial ring to be strongly graded, I think you need this idempotent to be full, but which is still guaranteed under these hypotheses. But that's just one thing.
Yeah.
And so yeah, I was actually thinking about this, and I would assume the argument should go along these lines. So if the ring is strongly graded, you're making a comparison between graded modules of LE and ungraded modules of LE0. The functor is in fact given to you by Dade's theorem. And between graded modules, you have the shift functor. Between ungraded modules, you have this extension of scalars by alpha. So you have all of the ingredients at the module level. One would want to check that you apply K-theory to that diagram and it commutes. But in the proof of this, you actually use that once you pass to K-theory, you can represent every class of a projective module in a specific way. And in the same way, for graded K1, you also use that each element here can be represented by a unit. And I think that's the gap so far between saying something at the level of modules and say it at the level of graded K1, which is that once you pass to the graded K0 or K1, you have nice representatives. And concretely, you can represent things like either idempotents of LE or units of LE. And that makes the computation possible. Of course, I'm not saying this cannot be done at the module level, but that is the difficulty I had between translating the statement at this level and at the module level. Yeah, anyway. But as Willie says, I suppose this should be the idea.
All right. Thank you, Guillermo, for that notes. And by the way, he has sent some, I think, references in the chat. Feel free to check it out. So are there questions? I have a question, and I apologize if this was answered throughout this conversation because it's kind of noisy here. But in a nutshell, how would you say the primitiveness was like essential in everything? And is the primitive, what do the primitive index, the lowest n, show up somewhere?
Right. Yeah. No. The lowest such n does not come up anywhere. So sorry. Let me see if I can annotate. Can you see this by any chance?
Yep.
Okay. Right. So the primitivity came up. We wanted all of these idempotents to be full. So EE star for each E and E1 for the algebra LE. It is true that I did say we needed this. I did not say where did we use it, and that's because the step where it occurs is a bit technical, but I can maybe write something down. So the point is, if we have a map between Leavitt path algebras, and we know that all of these are full idempotents in the degree 0 component, then all of these are full idempotents in the degree 0 component of LF. And so, again, this is maybe a bit technical, but we had some group here, which was some graded Grothendieck group of the duology tensor, some graded group of LF. And we can produce a map from here to there, which comes from E0 copies of K1 of LF. There should be an app. Now, the source map between the graphs gives you actually a map from graded K1 of LF to the E1, which we could actually write as a product indexed by the edges of K1 groups. And the essentiality part came from the fact that graded K1 of LF, well, again, by the fact that these are strongly graded, is ungraded K1 of the degree 0 component. Now, if we have such a full idempotent in the degree 0 component, so that's where the essentiality, the primitive part comes out, then this can be expressed like this. So I don't know if this was, I don't know if this answers your question, but the point is that we can now relate this to a package of units in the degree 0 component related to a morphism. Each time we have a morphism between Leavitt path algebras, we can build an assignment between a package of units in the degree 0 component, because these are our units, and an element here, and this group was the one related to our universal coefficients here. So I don't know if your question was about primitivity or essentiality or.
No, thank you. Answered perfectly. Thank you. Any further questions? Okay, if there are no other questions, but if you have, I think Guido will be very much okay to receiving emails of any further questions. So if there are no questions, I would like again to thank our speaker, Guido Arnone, for being the very first speaker of this series. Thank you so much from the bottom of our heart. And thank you for everyone who is here right now. And yeah, I think that's it. And see you all somewhere. Have a pleasant evening. Thank you so much. Bye-bye.
Thank you very much for the invitation.
Thank you. And the recording will be posted in the YouTube channel of RCTP. All right. Bye-bye.